Thank you, Sally.
Thank you.
So next week, across the world, scientists are going to be looking at their mobile phones nervously. They're going to be ringing home and saying, has anyone left a message for me? And the reason why is that there's going to be a few phone calls made from Sweden telling people who's actually just won the Nobel Prize. This is the prize that if you're a scientist, you're going to sell your grandmother, you're going to do anything to get this prize. And it's an amazing moment. When I was a journalist, it was a badge of honor to try to get to the Nobel Prize winner just after the committee had made the call. So Andre, let's go back to 2010. It was just an ordinary day, so you thought, in October. What happened next?
I was not anxious, and I didn't try to sell my granny. Actually, when people talking to you for 2 years saying, live long enough and you will get it, okay, you kind of get relaxed. And
you felt it was inevitable, even then?
You never know. First, I'm a physicist, and people were talking about Nobel Prize in chemistry, which I, would take it, but with some grudges.
Hang on, I'm an ex-chemist. This is outrageous. It's the queen of the sciences.
Condolences, okay. Anyway, and frankly speaking, at this day, I have forgotten that it's the day of Nobel Prizes, so I slept well, I was not anxious. And then there was a telephone call. I pick up a receiver, and some person tells me it's a very important telephone call with a Swedish accent. And my reaction was, "Are you going to tell me that I won the Nobel Prize?" The lady was shocked and saying, "Please don't hang up. It's not a hoax call. You will speak with someone whom you know." And then there was a person whom I did know from the from the Swedish Academy, who told, yes, I did win, so it was an ordinary day until I came to work and all people started congratulating me. That's it, nothing special.
But normally the phone doesn't stop ringing everyone that you've had any interaction with in your past life. I've had Nobel Prize winners telling me about how ex-girlfriends that they had when they were 17 or ex-boyfriends, suddenly on the line. Did that happen at all?
During the next few weeks, I got plenty of calls from the past, from people about whom I haven't heard for 30 years. Of course, I acquired many new friends within the next two months, and actually I found about a dozen of new relatives. I'm not joking. This is true, yeah. Okay, absolutely true, yeah. So a good experience, yeah.
And tell us about we've all got this picture in our heads of the Eureka Moment. Now, with graphene, is there anything that corresponds to a Eureka Moment? Well,
if some people think about scientific discovery as continuous Eureka moments, it's certainly not. It's mostly quite a boredom, I have to say. It's you have to push yourself hard in order to get once in a while some actually exciting mode, and you got something like that. So there were during this the course of discovery of graphene, there were a couple of moments which I was really excited when we first realized that it's a very thin material we can produce. It was one moment, and then the second moment, thin material, so what? Okay, you think
but this is when you were using Scotch tape to pull layers off graphite, the stuff of pencil tips, basically.
Yeah, essentially, what happens? Okay, many of you know what pencil lead is. It's actually depends on how much graphite is there. You make a pencil trace, you get pieces of graphite all over your paper, and because graphite is thick, it makes it dark. If you take a magnifying glass and look carefully, you'll find out that not all flakes of graphite of similar thickness. So some of those are pretty thin. If you take an optical microscope and look carefully enough, you will find some transparent pieces. So essentially this material was in front of our eyes, literally, and under our noses for what, 500 years since people started using graphite. And we didn't know about this material to exist, that we didn't know not only this material, we didn't know that there is hundreds and actually a few thousand of those materials which are one atom or one molecule thin. So it's for a layman. For scientists, they use graphite quite regularly in their labs. I use it probably for 10 years. Usually people try to have a clean surface. You take a chunk of graphite, use a scotch tape, peel it out, throw scotch tape into a little bit, and study clean surface, freshly cleaved surface of graphite for many, many experiments. So literally thousands scientists for decades were doing this one, throwing the sketch, studying this piece. So what we did, pick up this scotch tape and leave away graphite. So people didn't realize that throwing scotch tape, they have thrown their Nobel Prizes as well. So this piece of graphite you put under microscope and see essentially immediately that some of pieces of graphite are transparent. And if you have a decent education, you know that metals, usually they're not transparent. And this was transparent and gives you an idea that it's very, very thin. This was one of Eureka moments. Then we started making some experiments with these thin pieces of graphite, and there were a few other Eureka moments which showed us that it's not only thin, that it delivers some interest in new physics.
And there's actually a new twist on this that you announced just recently, where you're actually now interested in what's left behind on the graphite. You've got single atom thick channels that you can do interesting things with.
Okay. Yeah, so how to explain this? Okay, let's go.
That's Andre's speak for you've horribly oversimplified what I've done, yeah. I think.
Yeah, okay.
You know what I mean.
Yeah. So essentially, okay, let's go to the scotch tape and the piece of graphite. So it took 10 years, yeah, more than 10 years to realize that all people took this scotch tape, and it's a very popular technique, okay, used by hundreds of groups around the world to fish for graphene, for single layer of graphite using scotch tape. Widely used, we use it. And we were not interested in what was left. Essentially what we can do now, take a piece of graphite, pull out individual atomic plane out of this piece of graphite, and what is left? There is a very narrow nothing, an empty space. So this twist seems to be obvious, but it's interesting to see what this kind of very thin, empty space can do, because it's again, when you go from our macroscopic world to this microscopic world, all phenomena becomes very non-trivial, okay? So Richard Feynman, some of you know the name, he said there is plenty of room at the bottom, referring to that phenomena at nanoscale quite unusual. He just said it. What we do in experiment, we see that indeed phenomena at this nanoscale are quite unexpected. Everything behaves very weirdly.
And basically, using these channels, you can now tap all sorts of... They're kind of atomic capillaries, aren't they?
Yeah, we don't know what to do with them at the moment, so we just see how they behave. We look how water goes. In research, I say I'm not doing research, I'm doing only search. So I don't know the answers. I don't know the answers.
So there we are. Watch this space, or watch this nano capillary, I guess.
Wow.
But I must... next week, when the phone rings on Tuesday morning and the physics laureates are identified, there's always a bit of fun among physicists speculating who's going to get the big prize. Have you got anyone you'd like to nominate first before the Nobel Committee?
I'm asked every year to be one of nominators for both physics and chemistry committee. To be honest, I didn't nominate yet anyone. But my favorite at the moment is exosolar planets.
The exoplanet.
Exoplanets, but I don't know who would the person to be, because usually when there is such a big field, people wait for a long time before most contendants die, and then only 3 or less left. Okay,
I must admit, I'm probably going to put my bet on the gravitational wave people, so we'll see whether they... that will be a very quick Nobel Prize. But I think,
would you like to bet?
Right, let's...
no, it's too early for this one.
Your favourite wine is a bottle of Amarone, okay?
Yeah. It will not happen this year.
So we're in this museum. One of the things that this museum does and the other museums do in the group is to actually inspire hundreds of thousands of children each year. And I think everyone's always fascinated what set you on the trajectory to become a scientist. Was there a teacher? Was it your parents? Was it an encounter?
I don't know. It's politically incorrect to speak about genetics, but I believe we all know that you inherit traits of your parents. So my parents were engineers, and with some material science, physics, and mathematics. My father was a professor of mathematics at some university. So. Probably this was important, and then eventually, I'm not telling any secret, when you go to school, your teachers encourage you to do something which you are doing well. And initially you start doing well in some subjects, and teachers encourage you better. You find yourself that you are doing exact science is better than literature or something like that, and then gradually there is a feedback, self-organization process in which society, actually we live in the society pushes you in a certain directions, which involves not only parents but also teachers, your schoolmates who come to ask you for questions, and so on. So it's a societal push into every one of you experience, even if you haven't noticed this, that you are pushed in the direction in which you can excel. This is it, as simple as that.
And one of the other fascinating features about your career is you've moved around an awful lot. You're born in Sochi in Russia. Your parents were of German origin, and you worked in Nottingham, Bath, Copenhagen, Holland, and then Manchester. Has this, sort of random walk around the planet helped you in some way?
The longest, despite my Russian accent, the longest time I lived on this planet was in Manchester. I'm already 15 years. I'm saying it's too long, but haven't thought about moving to anywhere else yet. Okay, it's lovely city. Okay, it's so great to work here because it's raining all the time. So
no distractions.
No distractions. Indeed. So it certainly helped. Okay, I always felt myself being born to German parents in Russia. In Russia, I was never called Russian. Okay, first time I was called Russian when I visited Nottingham in 1990, and people say, "Oh, we have a visiting Russian here." I said, "Who is this?" etc. Because in Russia I was a foreigner with a kind of weird surname with r, which is I speak, which is also unusual. So I was always an alien on my own, and on my own among aliens, as sometimes I speak. Okay, this certainly helped me to form who I am. Okay, for good or bad, I don't know, but it's an unusual trajectory indeed.
So the relentless rain of Manchester, that's one key factor why you're here. But what about the research landscape here? How does it compare in the UK compared to being back in the Netherlands or Russia again?
Well, I remember when I came in Russia, it was complete demise of the Soviet Union. I vividly remember I came to Heathrow Airport and I had £1 coin in my pocket, and fortunately someone from the Royal Society met me and we had a traffic accident at that in the first hour of my time from Heathrow to central London. Okay, but doesn't matter. So yeah, it's I came here just as a visitor because I was okay, not really high flying, but okay. In Soviet Union, it was opportunity to come to Britain, and then I spent half a year at the University of Manchester, and it was kind of an eye-opener because at that moment I realized that what I was doing in Russia, I was wasting my time trying to do whatever, not on competitive level, and there was a possibility, University of Manchester, not Harvard or MIT or even Cambridge, but there was a good lab there, competitive facilities. You combine, you may be not most competitive, but combined with some intuition and some knowledge, you can become world competitive, and there was no way back. That's okay. It's not economics, it's not that it's more than one coin a pound in your pocket. It's really possibility to realize yourself. That was important motivation factor that I moved to the West.
And what do you make of Brexit? Because I'd be fascinated to get your perspective on, because there's been a wave of horror really from the scientific community about the prospect.
Well, okay, first thing, when we will know what Brexit really means, okay, then we might speculate, but I always said, okay, before breakfast, okay, I didn't meet Boris Johnson, but okay, imagine you go to a doctor and doctor tells you, I have an excellent medicine for you, you'll try it and you will be much healthier. I would ask, did you try on yourself? No, I didn't try on yourself. Did you at least try it on frogs? No, I didn't try it on frogs at least. So I think we scientists, we always try new medicine on frogs, and I think this country is too good country to be the first to lead the way of trying medicines on ourselves. So this is okay. This is unbelievable what happened, but okay, we'll live over.
Well, come on, I mean, this is search, not research, Andre. You see, we're venturing off into the great unknown here. I would have thought you'd approve of this with your adventurous spirit.
No, but I like to base my search on the previous knowledge, and there is no previous knowledge to this one, so okay. I repeat, who was that? It was Bismarck, Chancellor of Germany. more than a century ago. At that time, socialism was a very popular idea, and Bismarck, everyone was thinking capitalism gone, socialism, Marx, Engels, and so on. So Bismarck was asked, what do you think about socialism? Like you're asking me about Brexit. And he said, it sounds like a great idea, but I think this nation is too valuable. Let it be tried on some less valuable nation. So.
And when you say frogs, did you mean the French here? No, you don't have to answer that. Let's move on to you've got a very adventurous approach to science, and you do this thing, Friday night experiments, where you try off-the-wall ideas. Just tell us a bit about the kind of things you've done and what you're thinking at the time.
Academia is a tough life. You really need to be competitive. Until you get a tenured position, you really can't afford yourself, some random experiments or anything like that. You focus on publishing to getting grants and so on. And I was not different until I get associate professorship position, which would be reader in this country, and then after 3 years in the Netherlands I got a bit relaxed and thought, we in academia are not that well paid to do boring stuff. Let's do something for our soul. What I'm curious, this is what we are taught at school, that scientists do, great things. What in reality we do, I actually quite a boredom and have to follow this rail. Usually you start from your PhD studentship, and then if you are successful, you get few papers, you got postdoctoral associates, and if you're successful, you got another level permanent positions there, and this is from your scientific cradle to your scientific coffin, just a straight line. Step left, step right.
I hope there aren't any scientists in the audience. You must be feeling a bit depressed now.
You're gone. That's life. But then you want. Let's remember. What we were taught at school. So I start thinking, what can I do? Something around about something which I never dealt in my life. And one of the first experiments, can you actually show slide number 1 if possible?
Yeah, we've got some slides to illustrate one of Andre's Here we go, Andre. Sorry, I'm looking that way, you're looking that way. That's
fine.
Right.
So in the Netherlands we get these kind of facilities, which actually were there for 40 years, and they were quite awkward, and at that time I was quite conscientious about helping your lab to do something good. So I thought, what can I do with those facilities? No one actually using much, and I thought maybe I can study what happens with water in high magnetic fields. Absolutely no relations with any of my research whatsoever. Completely different area. So once upon a time, I said, why talking about this? Let's pour water inside. Literally switch the magnet and pour water on top of this quite expensive scientific equipment, frankly speaking. So you expect water to end up on the floor. Instead of this, after, do we have a movie? I don't know why it's not moving. Movie is not going. Instead of this, we get a water levitating in the middle of the magnet. I was well educated to realize that it's not anti-gravity machine, but something quite simple. But what shocked me after this was that no one of my colleagues who professionally for sometimes 40 years worked with high magnetic fields, they never tried not only this experiments, they thought that it's a hoax, that I just pull in their legs and so on. So they asked me to show. I showed that and then we don't have movies, unfortunately. That's a pity. And they came up with the brilliant ideas. What else we can levitate inside magnetic field? Everything went there. As you see, strawberries, tomatoes, potatoes. Okay, you name it. And after so that was kind of. The phenomena behind is quite simple. Its diamagnetism was known for 100 years or 125 years to be exact, but people thought it's so weak phenomenon that nothing can happen, even people working professionally. So that's essentially it.
Let's move on to the frog, because we got a question by Twitter from Len Fisher, who said, why is it that, now this is the work that got Andre the Ig Nobel Prize, which is a kind of spoof. Oh look, here we are.
This one moving,
here we go.
Everything else is not moving, so that's a frog.
But Len asks, why is it that the levitating frog you're more famous for that than you are for graphene and so on?
Yeah. I don't know, okay, because this is not only. At some moment, I ended up in a hospital after misadventure in Grand Canyon and so on. So I ended up in Flagstaff Hospital with pneumonia and snake bite and so on. And next day, I have become very popular because people tweeted me. I suspect they Googled me. I suspect they wanted to know whether I can pay my American bill or not for my treatment. But immediately I got a queue of people who came and said the frogman, and etc. etc. No one cared about graphene at all. At this time I was third Nobel Prize winner, but was known in the hospital among beautiful nurses there as a frogman. What is strange is actually at a conferences where academics are around, okay, I still meeting people who say, hey, I know you, okay, I have no idea what graphene is, but you're frog.
No, Andre, you can relax. You are not the frog man to me. You are the hamster man. And in fact, you must show us the next slide, because this is one of my favorite scientific papers of 22 years of reporting. If we can get it to come up.
Okay.
Oh no, we can't get it.
Okay, can we move on? Okay, we can.
That's it, now.
Okay, that's the paper, and it looks an ordinary paper. It's the second author is someone with a very Dutch name, Tertisha, until you look for initials, and it's not a joke, actually.
Look, stop laughing. This is serious science.
No,
okay, come on.
It's okay, paper, and honestly, this guy deserved to be on this paper because, unlike some of my colleagues, he really participated in those experiments and helped a lot with this one. As you see, actually, if there are animal rights activists, I have to say that it was the first hamster I was dealing with. It was very small baby hamster, and after the experiment, my wife took him home, and he was so lovely. So I think we still have hamsters. We still have hamsters, slightly different type in our home. But what is unusual about health effects of this one. If you're worrying that usually those hamsters live 1.5 to 2 years, this creature lived 2.5 years. So I'm thinking if the magnet would be big enough to levitate myself, maybe maybe increase my lifetime to 120 or something like that. It was 120 hamster years he lived. Okay. No. I'm scientist, not any conclusions about one experiment need to be reproduced.
But you've already mentioned the snake bite incident, and you, in fact, you emailed me a couple of weeks ago saying that you cracked a few bones in the Alps. I mean, is this you're just an adventurous person? You like physical thrills? You like scientific thrills, or is there no connection between the two?
Well, I don't like those experiences, especially, they all sound good after you've survived those experiences. The most dangerous one, when I was bloody stupid, when I was 32, something like that, went to the Caucasus and decided that I know mountains so well that I went on a glacier without a rope. I used to fall into crevices on a regular basis, but it was with rope that time. Okay, it was without rope because I felt that I'm strong expert. So fortunately, I ended up on a ledge only 10 meters below, rather than 2 meters left, 5 meters right, and I would be not talking this one. Yeah, still gives me nightmares, but okay, it's a detour from our conversation. Yeah, I think it's, I always say and like to repeat to people, like I said to you before this evening, that I measure life not in years but in experiences, and I think I recommend everyone to live to the full, whether it's scientifically or in terms of adventure. It's interesting to remember those experiences, especially afterwards, if you survive.
Now, I've got an interesting tweet question here from @Rose_Isabel, who says, how have your feelings about graphene changed over the last 12 years? And I wondered, are you a bit bored with graphene? Have you moved on, or are there still exciting things to explore?
Well, graphene is now shorthand for many other materials which are similar to graphene, one atom or one molecule thick. So initially we thought it would be just a very good scientific paper. I'm not that smart to predict 10 years in advance, what would happen. It was good, I knew that. Exceptionally good, I knew that. But only 3 years later, when new properties of the material, the thing is strongest, most conductive, thermally conductive, impermeable, and there are so superlatives to these materials, then you realize that it's an exceptional. So this is graphene 1.0, as I call it. I stopped doing this, even before Nobel Prize, essentially. 2009, 5 years, 1,000 people doing this. You try to go away if there is only little space, a Lee left, and on this Lee there are 1,000 elephants who are looking for a piece of grass. So I moved away to what I call graphene 2.0, which is trying to find another material, one atom or one molecule thick, which brings us new properties. So I moved away, and a couple of years later, what we're doing now is graphene 3.0. Again, shorthand for graphene because it's similar type of material. So what we're doing, we disassemble, similar to the Scotch tape technique I described, disassemble layered materials into individual atomic planes and then trying to reassemble them into something which nature can't provide, layer by layer in a design system to find something interesting in those materials. So it's new kind of materials we can build layer by layer. It's like Lego game, but Lego game played not with those cubes, but with individual atomic planes. So we moved very far from original graphene.
That very neatly takes me to another tweeted question from @NegativeNeutron, who says, of all these new two-dimensional materials, which of the other materials do you think will be the most revolutionary or most exciting?
I think, I'm sorry, this question doesn't have much sense. The most exciting, exciting that those materials do exist, as I described before, they were in front of our eyes and under our noses for centuries. And if it would be graphene, despite its kind of many superlatives, it will be still a single material. That now you have a variety of those. I thought we have 200. Okay, a couple of weeks ago, someone looked at possibilities, and there are something like 2,500 of those materials, some of them even not studied. But this library of materials makes this really huge, you know. It's probably a little bit ambitious to say, but more and more people start thinking about this. There was age of iron, bronze, stone age, and so on, age of plastics, aluminum, and now arguably we're living in the age of silicon, with so many two-dimensional materials, as we called it, because they essentially have no thickness, because they're as thin as possible. With this age, people thinking that we are now at the beginning of the age of two-dimensional materials. And yeah, one of the superlative of these graphene-like materials that usually takes 20, 40 years to move from academia to industry. Suddenly, within short 10 years from the first paper essentially on the subject, already we have graphene products where graphene is slightly improving properties. It's not only in industrial labs, it's now in consumer products.
Well, I think before I bring in the audience to ask some questions, let's just drill a little bit into the applications of graphene, because you've talked to me in the past about the kind of dirty and first applications, and we really are beginning to see those right now, aren't we, in products? I mean, give us some examples of the sort of things that are out there.
You know, it looks to be these two-dimensional materials promise to be disruptive technology. No industry likes disruptive technologies. For the definition, what is disruptive? Because there is a process you need to report to your shareholders. So the further down the stream, it's better for the industry. So industry is not very good in innovation in this case. But you need, if you promise something, you need to give something back. Money invested. And the first step, as it's happening now, people, thanks to China, actually, frankly speaking, people develop mass production of graphene. They have no idea what to do with this graphene, but local governments, it's not like 50 millions given to Manchester by the government. Okay, actually 38 millions given in Manchester, which is welcome, but you need to compare it with other countries where much bigger money. So local governments poured money in the production, and people produce graphene. And what happened? Industry had a possibility to buy graphene not from academia in grams, milligrams, or even kilograms. They can buy in tons and put it into different products. What happened, for example, people took this graphene, put it in batteries. Not much happening. Improvement, 2-3% in the capacity of the batteries. It won't much different for you if it's in mobile phone, but if you are electric car manufacturer, it gives you a competitive edge at something like 10 cents per battery, 10 pence per battery, and its improvement 2.3%. Another one, okay, more actually on the exhibition, which is Manchester involved, we put graphene on the back on LED lamps. And to our own surprise, I thought it would be a gimmick, slight improvement, 1-2%. The lifetime, you take the same LED lamp with graphene and without graphene, it improves just, I don't know, milligrams of graphene paste, decreases temperature by 15 centigrades in certain cases, and the lamp, like similar lamp, serves with graphene, serves twice longer, and in addition, we found that its age is slower. For the same luminosity, you get savings like over the lifetime of 10 pounds in electricity cost. So this kind of trying to add something to tires, to plastics, and so on is the first step. It's not revolutionary. People even don't call this graphene-based or rarely used, but it improves things a bit. But what is important, graphene now pays back to investors, and now has become a golden rush for graphene investors because they see that it's not only investment, it's paying back. So it's the time, seems to be we're at the time of snowballing commercialization of graphene as well.
And of all the more radical uses of graphene, like, for example, you work with colleagues in Germany and Austria on a sort of artificial atom that was purportedly could be used as a unit of a quantum computer that would have radically new properties. I mean, what sort of, I mean, is that going to be the real graphene revolution, or do you think it's going to be something quite unexpected?
Well, if we would know where to dig gold, we will be always with our shovels at this particular place. At the moment, we don't know where real applications will be. So a lot of people speculate in where applications would be, and it's on the basis of our earlier knowledge. What is usually life shows us, and this is what recent development in the last, I would say, 3 years, before it was all speculations because there was no production. The life tells us that applications are in a completely different area where we could expect those. One of those which I really like, you're talking about quantum and etc., something which would aspire layman of your newspaper, your former newspaper, something you don't understand inspires people most, okay? That's the usual stuff, but it's so far, it may happen, but it's so far behind horizon that we can't really judge whether it will happen or not. But for example, okay, about 10 years ago, about 4 or 5 years ago, I thought it would be great as a first application would be graphene tires. And I thought graphene is strong. Soot, carbon black is used for production. Let's put, instead of this carbon black, let's put a bit of graphene. I even gave interview, I wrote somewhere that would be great to have stronger tires. I was both completely right and completely wrong. So people did put this in tires, not looking for my advice. Essentially, it's obvious where you can, one of this direction you can go, and then found out that indeed, tires, they're expensive at the moment, but they serve 2-3 times longer. Not because what I thought it would be stronger. It has nothing to do with strength of graphene. But the rubber becomes much more thermally conductive. So why rubbers become ball? Because you break, tires get hot, and they shred layers by layers of rubber. In this case, the heating is less, so the shredding of the rubber is less. So they serve, people say in already industrial tests, they serve 2-3 times longer. If this is done, all investment in graphene, you know, millions and billions of tires which are thrown away every year. If even these single applications would survive. I think our research is well vindicated.
Well, we've got a couple of roving microphones to take questions from the audience, and I'm going to get them queued up now. So if you put your hands up, do stand up and say who you are so we can pick up what you say on audio. And I'm going to just ask one more question that was put again to Andre on Twitter. In fact, it's from two different people asked kind of the same question while the mics are being lined up. One from @JamesMoff and one from @JamieLee. And they both asked, what's next? And I guess, and what are you doing in your Friday night experiments? You know, if you're not levitating more, you know, bananas or something like that, are you? No, well, you must move on, I guess.
Yeah. No, I probably answered this question. I'm constantly looking for a new field, and this Graphene 3.0, it has nothing to do with initial graphene. It's reassembling using. Essentially, we have a new toolbox now, thanks to graphene, and now I'm using this additional toolbox to find something new. So because I'm using this toolbox, as many other colleagues do, we're all called graphene researchers, while there might be nothing at all in our experiments with graphene. These two-dimensional cavities, empty two-dimensional space has nothing to do with graphene, but we are still consider our graphene researchers because it's the motivation which was given to us and many others. So I'm doing two-dimensional water. Does it have something to do with graphene? Yes and no, but it's completely new subject for me. I'm enjoying learning new things, but it's a gold mine there with possibility of these materials, and you don't want to completely leave this gold mine because so many new things to be discovered.
Well, we're not going to dive into two-dimensional water. We're going to take our first question just over here. Do say who you are, and do stand up as well, actually.
Hi, my name's Colin, and as an electrician, I got to work on the Graphene Institute, so I got to see what a fascinating building that's now become. And I wondered if you could just talk a bit about the Graphene Institute and maybe particularly the research topics that are going to be happening there.
So what was the question?
The Graphene Research Institute and what in Manchester, the National Graphene.
National Graphene Institute, NGI as we call this. There are many different peoples. Most of people work on the subject I described in my talk, graphene-like materials. People are looking for applications of graphene and graphene-like materials, trying to push it from science into some industrial applications. Essentially, National Graphene Institute, it's a collection of individuals, academics, which cluster around new facilities. So it's a very high-tech facility, I have to say. It's very strongly competitive at the moment. We're at very early stages, but Nobel Prize and etc. All this research has been done in much smaller facilities, but it looks all good. This facility is investment for the next, I don't know, at least 30 years in front of us. So many people can compete with the best places around the world, and in terms of material science we have extremely competitive facilities at this National Graphene Institute.
So Manchester can lead the world in graphene, I think, which is rather lovely.
Not can, we still do.
We do. Sorry, forgive me, Manchester. Let's have the next question.
Hi, my name's Chris. I heard that you were talking about graphene can also double the life of batteries as well as tyres. Now that sounds all well and good, but then you've also got to think about the cost. So when will it be affordable for like the common family?
When will those tyres and those bulbs become affordable? I mean, are they
bulbs? I think you can buy LED lamps from maybe 1 or 2 months from now. They're already in production and delivered to some customers around the world. I know some company in London ordered 50,000 of those. They just in production for the last 3 years. It's tiny improvement in quality, but valuable improvements. Tires, I don't really know. I hope it will happen, but it's still a bit expensive. As batteries, graphene improves not twice, but 2%. So I don't really know whether it's possible. We don't do in Manchester batteries, or not much, let's say, but there are hundreds of groups around trying to improve battery life. I'm pretty skeptical that if it will be a factor of 2 ever, maybe it will be more than now, than few percent, but whatever. So I'm at the moment, okay, what I see in future, maybe except for tires, it's slight improvements of things. It's not really revolutionary. It's not time has come for something truly revolutionary. People we know the properties. I'm an academic, I know the properties of graphene. Now what industry is doing is trying to improve their things with adding this material through maybe there will be other applications. I was a week ago in China at the exhibition of commercial products which are graphene based. Half of them are gimmicks, okay, which I don't really, they put word graphene there, but whether it improves quality or not, I don't know. But the other half is truly improvements of, in one way or another, all happening in tiny fraction in costs, and it improves a little better our life. I don't want to speculate what will happen in 10 years, but this is what's happening now.
I seem to remember there were graphene condoms as well. Whatever happened to them? Sorry to lower the tone, but I'm intrigued.
I refer you to my colleagues who are dealing with this one, okay?
Let's have our next question.
Hey, we're part of the Graphene Society at the University of Manchester, and last year we learned several times, or we were told several times, that normally in science apparently you've got an issue and you think what can we use to solve this issue, but since graphene has appeared the role's kind of reversed, and we've got graphene now, and how many issues can we solve with this material, how many things can we do with this material, and I just wanted to ask you a bit what you thought about that.
So it's the thing where we've got a material, we've got a solution for problems that we don't really quite understand yet, I guess. It sort of reminds me of when the hologram was first unveiled and things like that.
Yeah, it's there is an airplane behind you. Okay, so there was aluminum. It was discovered nearly 200 years ago, light, strong material, fantastic material, people thought, but what to do with this? And people didn't know what to do with this material until airplanes appeared. Then there was really, now we can't imagine our world without those kind of materials. So we were really still waiting for real applications of graphene, something which would really be so competitive that nothing else can compete with this material. But it usually takes time, and production is not really solved the issue. So what is nice at these situations, so after short 10 years, and especially 3 years since mass production was solved, we already now have real improvement in some products, and it's very important because it allows this snowball feedback effect that manufacturers see that some venture capitalists see that something comes out of this material, and it gives a feedback and more investment going on. But at the moment, okay, I wouldn't try even to speculate about any revolution. It's just gradual improvement. We don't know whether the revolution would be the same situation which was with aluminum, with plastics. Polymers were also known for a long time. No one cared about those. Silicon was for 60 years. It was known, studied, but no one really knew whether it will bring some application. So I try to downplay maybe a little bit expectations, but I would be happy even if we improve all things around us, not by a factor of 2, but by 10%. It would be great.
I realise I've been neglecting this half of the audience, so let's have a question from over here.
Hi, I'm a volunteer in the exhibition upstairs, and what a lot of the visitors are particularly captivated by is the simplicity of the whole sticky tape method of isolating graphene. And may I please ask if you could elaborate kind of more on that moment of the isolation? Like, was there a spark of inspiration when you thought on the sticky tape there could be graphene, or was it more gradual than that?
I think it was, we tried a little bit different experiments. The original idea, I checked my CV before 2004. I never mentioned word graphite or carbon at all. So the idea was to make films of graphite as thin as possible, but and it didn't work well for a few months. Frankly speaking, nothing did come out. And then suddenly we saw on the Scotch tape pretty thin pieces of graphite which were transparent to light, and this was kind of Eureka Moment. But it's a bit of a legend about this. This is how it happened actually, but people put an emphasis on the simplicity of technique, okay, like everyone can take a piece of graphite and Scotch tape, and even, I don't know, in the fourth world country, people just supply them with enough pencils and Scotch tape, they can win Nobel Prizes. It's a myth perpetuated by journalism, essentially.
He's so hard on journalists. Have you noticed this?
Well,
I'm getting this needle.
I know many of them. In a sense. So in order to compete in this world, you really need to have top-class facilities. Why US wins so many prizes and so on? Because they have best university facilities, and UK has very high, especially life science facilities in this world. So the first stage of making something thin wouldn't bring you a Nobel Prize. It would be an odd research even if you managed to publish it. The really hard part was to show that these pieces on the Scotch tape show some extraordinary properties, and this was a hard work for 4 or 5 years, trying to be in front of all other people who try to get a piece of this cake, and we were quick and so on, and many of the properties, if not majority, is attributed to the work of our group. So it was really hard work requiring background, knowledge, and also high-tech facilities, which we fortunately did have. There was when I came to Manchester in 2003, we got good science minister Lord Sainsbury at this time, and I got my first grant, about 1.4 million, to set up a small facility. Without this facility, there would be nothing. We would be outrun by other people. No one even considered us. It was important to carry on with this research. It gave us a force start with respect to all other groups, but it was important to elucidate those properties rather than just say, hey, we have graphene, very thin material here.
So that Eureka moment is more of a myth than reality, I think. Let's have another question from this side of the audience. Again, do fire away.
Hi, Adrian Nixon. Graphene production at the moment seems to be on the scale of making it in large quantities, but lots of little bits. How long do you think it'll be before you could make it on the scale of, say, carpet, so you could maybe test out your hammock thought experiment?
Graphene hammock. That sounds good.
Well, we have very small hammocks around. Initially, smaller than cross-section of your hair, but now probably in millimeters of sizes. Of course, it's very fragile material, but remember, it's one atom thick and still withstands. You can poke it with your hair or with a match, and it's still not breakable. It's breakable, but if you're careful enough, it won't break. But you need to remember that it's thrown only on nanoscale. No any other material can survive this kind of environment and trying to move it around. But talking about mass production, you're right. At the moment, industry uses so-called flaky graphene, which is one atom thick, but comes in micrometer sizes and put in different products. Actually, a few years ago, a production of graphene in square meters or square kilometers has been developed. It's pretty expensive, kind of $40 to $100 per square meter. You can make it, and quality is not exceptionally high, many defects and so on. So people try it on mobile phones, as a touch screens on mobile phones. You can buy those graphene touch screen phones, at least in China. They're not, frankly speaking, any better than the touch screens we have now. So it's a question, as with industry and industrial product, a question of cost. For example, if indium becomes twice more expensive, then it becomes competitive and so on, and really no exception. People haven't thought about some exceptional property, exceptional product where you really need graphene and other transparent conductive materials won't do. So we will see for specific application, but this has been developed. If you need it, it can be done.
Let's have another question from this side. Fire away.
Hello, my name is Prashant Thakar, and I got a couple of questions related to the application of the graphene, but currently I can't disclose that all the information due to the legal reasons. But I just wanted to know that this particular the graphene material properties are being tested on the realistic atmosphere.
Were tested in
in realistic atmosphere, from the sun's heat to the ice cold temperature sort of things. Does that the properties differs from the original invented properties?
Yeah, how do the properties of graphene vary over temperature and pressure and things like that?
It has been all tested. Original experiments were done under ambient atmosphere, and yes, there were experiments which were done in vacuum, at liquid nitrogen temperatures at 1,000 Kelvin, everything at 1,000 Celsius. Everything has been done and tested. We know actually practically everything about graphene under different conditions, what possibly can be known. It's thousands of groups all over the world tested this material and under all possible conditions.
And given it's so simple, does it actually match you'd imagine the theoreticians would have predicted these things. Do you get a good match between experimental properties and theory, or there's some weird anomalies that might be worth looking at?
Initial theory of graphene was developed 60 years ago because graphene is so simple. So this theory was developed to understand properties of graphite as the simplest approximation, as a stack of graphene sheets. Graphite was very important material for nuclear industry and so on. So people did develop some simplistic theory, but as usual, okay, everything based on, in theory, based on guesses, on approximation. This is why you need experiment. No computer can predict the complexity of the world, and then when you have the real material, experiments show unusual properties. People didn't think about this, especially most people don't think about materials. They think they won't exist even in principle. So there was a whole zoo of unusual phenomena people could test with this material. Essentially, our contribution was mostly in electronic properties, which appears completely anomalous with anything else, gold, copper, or anything we know. It's very interesting. It's a little bit academic research, but it's no theory could have predicted what we have found.
Let's have another question from this side. We've got a few minutes, about 5 minutes left until the end of the event.
Les Barstow. Question more on the human level, and that would be, you're obviously a dedicated and focused scientist. Did you have any ambitions other than entering a career in science, either when you were at school or perhaps midway through your education?
Well, I'm quite sane person. I have never thought about winning Nobel Prize because you know, it's hard work, of course, hard studies. You need to be adventurous. This all helps, of course, but it's also a big chunk of luck which you have to rely on, because there are 5-6 million of scientists around the world, and 1% at least of them are very smart people. So it's a very...
Only 1%? Oh, I don't believe it. What, 99% are not very bright?
I said very smart. 99% are smart people, but exceptionally.
You can't get the journalist out of me, Andre. You know this.
So, yeah, it's tough competition, essentially. So I didn't have an ambition of winning Nobel Prize. I have an ambition of doing science because, as I told you, the society, my environment, because I was good in, I had an excellent memory until I become a student and have drinking too much, and I could memorize actually a dictionary or something like that in just a matter of days, and then forget during the next 2 days. So I had an ambition to become a professional in science, or maybe math. It was a possibility for me, but no other ambitions. But then, during the lifetime, when I said I came to Nottingham, I realized that I can be competitive on international level if facilities are appropriate, maybe not the top facilities, but competitive facilities. So ambitions are, of course, there, and it's important to be ambitious. If you can't succeed in science, because if ambition is not there, you are not competitive with respect to your colleagues. So, yeah, okay, I don't know what my ambitions now. Okay, I'm not sure, because I accumulated probably so much inertia over the years. So I just carry on doing research, because I have found, okay, Nobel Prize haven't distracted me, because Usually Nobel Prizes are given for people who have done their research 30, 40 years ago and they enjoyed quiet old age pensioner life and go to give talks and to teach young people how to win Nobel Prizes and so on. Okay, I'm not patronizing anyone. It's a lot of luck, and I'm not interested in this kind of post-career, I would say. I know what I'm doing good, and I'm still very good at research. Maybe my memory is not as great as when I was 16, but I get a lot of knowledge and I know how to combine things. I often compare scientific research, the type of research I enjoy, with Sherlock Holmes stories. You know, you have some hair on your clothes and you have some odd lipstick, okay, some dust on your shoes, and you guess who is the criminal and who is the victim and so on. So top-level research is something like this Sherlock Holmes detective ambition. So you get very few clues initially in your experiment, and answers do not come immediately. Who is the criminal and who is good one? You need from those very few clues to make the whole picture as a puzzle. You know, you see random lines and then someone tells you it's a face of your person and you say, oh, indeed, something like that. So this is what I'm probably good at, having very few clues, see a bigger picture a little bit earlier than others. This gives me a competitive edge and I love this job.
We've got time, I think, for one more question. Let's go over to this side.
Hello, my name's Michael O'Loughlin. Just two questions, really. Is there any way of controlling the porosity of graphene as for, say, desalination? And can you see a two-dimensional fabric of the future that could be used to reduce radioactive decay, possibly?
Yeah, all those applications you just mentioned, desalination, filtration, make some polymers filled with graphene. This all has been discussed in literature, initially speculations, but now it becoming the reality. Desalination is very popular subject of research. I'm involved a little bit into this research. I don't think that there would be major breakthroughs because of some fundamental reasons, but it's an interesting subject. Maybe one day, I always hope that we will get some handheld device where you put seawater and get, after 5 minutes of pumping, you get a glass of drinkable water. And this kind of things possible. As concerns plastics filled with graphene, it's already a reality. There is a graphene car, which is called Graphene Car, produced by some Northwest company, where it's not much graphene, but the top layer of the surface of this sports car contains graphene composite, which slightly improve performance, slightly reduces weight, but it's an important, those several percent improvement, which makes one sport car different from the other sport car. And people all over the world actively now produce these graphene-based plastics and improves performance for airplanes, for cars, lighter weight, and so on. This is very close to the reality, if not the reality already.
Well, I think yet more evidence that graphene is indeed a wonder material. Do see the exhibition. Thank you for those brilliant questions, both from the audience and from Twitter. Thank you to BBC Focus magazine for the live streaming. Thank you to the Museum of Science and Industry and to Sally MacDonald for the introduction. And she's asked me to remember that next month is the Manchester Science Festival, which will be a brilliant event. And finally, let's have One round of applause for the great Geim. Thank you very much.
Thank you. Thank you. Thank you.